Hello everyone, my name is Leonardo and today I'll present our work investigating pre-trained language models for graph-to-text generation. This is a joint work with Martin Schmidt, Heinrich Schutze and Irina Gurevich. So in this work we are interested in the task of graph-to-text generation, where you have a graph and you'd like to generate a text that describes the entities and the relations between these entities in the graph. In particular, we explore two kinds of graph. The first one are knowledge graphs, so where you have entities that are connected by some relations, and this is the text that describes or represents the knowledge in this knowledge graph. And we also explore abstract meaning representations, where you have a semantic graph that describes a sentence. So previous work for graph-to-text generation using pre-trained language model, they usually employ autoregressive models where they use the source graph, a linearization version of the source graph as context. So in this work we are interested using conditional language generation. That is, we'd like to use not autoregressive models, but models based on encoder-decoder architecture in order to encode graphs and generate text that describes those graphs. And for that we investigate two pre-trained language models, namely BART and T5. So one important step when you are working with graph-to-text generation is how to feed the graph in those models, right? And usually one way to do that is linearizing the graph. So you can use some algorithm to linearize the graph, for example using a DFS algorithm, or for example extracting triples in this graph. So here we have an example of a linearization of this graph, and here you have another example of linearization. Finally, we fine-tune BART and T5, and for T5 we add a prefix, translate graph to text. Further, we explore task adaptive pre-training. The idea is collecting task relevant data to further fine-tune the model. So you have the original model with a pre-training. After that we do this task adaptive pre-training using additional task specific data, and finally we fine-tune the models in the final data set. For the task relevant data we use for silver AMRs, we use a parser to extract silver AMRs from gig word sentence, and for knowledge graphs we extract those knowledge graphs using a semantic scholar. So the idea is that we collect abstracts in semantic scholar and extract graphs or knowledge graphs from those abstracts. And we explore two ways to adapt the model in the task adaptive pre-training. One is a language model adaptation, where we use only the target text, so using BART and T5 objectives. And you also explore supervised text adaptation, where you use both graphs and text to adapt the model. We evaluate our work in three data sets. One is AMR corpus, another one is WebNLG dataset, and agenda dataset. We evaluate the models using different automatic metrics and also human evaluation. So here we have results for AMR and WebNLG. Because of the time we omit results for agenda, but you can check it in the paper. So first note that BART and T5 has very strong performance compared to previous work that use autoregressive models like GPT-2. Also note that our task adaptive pre-training further improves in different metrics like Blue, Meteor, and Blurred. For WebNLG, we see similar trends. So we also execute a human evaluation using Amazon Mechanical Turk, and we evaluate three different components: fluency, meaning similarity, and semantic adequacy. So first, note that our approaches are better than previous work in all of the metrics. Moreover, our approach score higher than the reference in fluency. So this highlights their strong language generation abilities. So the previous result showed that only with the linearization of the graph we achieve a very strong performance. So now we are interested in checking if the graph structure is really necessary. And for this experiment we shuffle the labels of nodes and edges after the linearization. So the graph structure will be obscure for the model. So let's say that we have two triples with head, relation, and tail. So here you have two triples and you just shuffle it. And you use these shuffled versions to train the models. So here we have results for T5. So T5 trained with the normal linearization and T5 trained with the shuffled linearization. First note that for knowledge graph datasets, WebNLG and agenda, the results don't drop a lot. And this suggests that the graph structures are not that influential for the results. However, for AMR, the performance dropped significantly We think that this is because AMRs are much more complex graph structures. So in this case, the graph structure is really more important than in the knowledge graph based data sets. So here we see an example of the original input for the T5 and the text generated by T5, and here we have a corrupted input where we shuffled completely the triples, and we trained a T5 model with shuffle. And you see that the model is able to generate a very fluent and correct text. So intuitively, those models learn the relations between entities during pre-training and fine-tuning. So in summary, we investigate two pre-trained language models for graph-to-text generation. We showed that different task adaptive pre-training approaches are beneficial for this task. And finally, we find that pre-trained language models may not always follow the graph structure, and instead using memorized facts to guide the generation. We can find our code in this link. Thank you very much.